In this lesson, we will learn how to choose a factoring method when faced with factoring a polynomial, and how we can factor polynomials that have more than one variable involved. So just to refresh our memory here, factoring by GCF, let's suppose I needed to factor the following polynomial. Well, the first thing I want to do when I'm factoring in general is take out the greatest common factor from all terms. Notice that the greatest common factor here for all four terms would be negative 2x. So I factor out that negative 2x, and I'm left with the resulting polynomial with four terms. Then I look here inside the parentheses, and my next inclination would be to factor by grouping. Okay, so I grouped the first two terms and the last two terms, and I looked for common factors in each pair of terms. So starting with the first pair of terms, I notice I have x cubed plus x squared, which has a greatest common factor of x squared, so I factor that out. And for the last two terms, I notice that there's a GCF of 3, so I factor the 3 out. So my result is this. Then, of course, I can finish factoring by factoring the x plus 1 factor out of both of these terms, and I'm left with the following, with one minor mistake. Notice I'm going to have x squared plus 3 times x plus 1, but I neglected to write in the negative 2x that I should have brought down here. So let me draw that in. So this should be negative 2 times x squared plus 3 times x plus 1. Okay, so let's suppose I need to factor this. This is a review. There's no GCF for all three terms, so I can't factor out a GCF. So the next thing I do is look to factor this thing into a product of two binomials, since there's three terms here, so I wouldn't factor by grouping. Now let's take a look. Whatever my first terms in the binomials are, they need to multiply together to give me my first term in my trinomial. So since 5 is a prime number, I know that my only possibilities are 5 and 1. So I would multiply 5n times n in my first product to get 5n squared. Similarly, 2 is a prime number, so I know that these last two numbers, which contribute directly to this product here, the constant term of my trinomial, so that my only possibilities are 1 and 2. So of course we could have paired the 2 with the 5n and the 1 with the n and still have gotten the first and last products to work out just fine, but if we look here, if we FOIL, you'll see that this factorization is indeed the correct one, because the product of these two binomials I find by using FOIL. I have 5n times n, that's 5n squared. My outer product, 5n times 2, that's 10n. Inner product, 1 times n, that's n. Last product, 1 times 2 is 2. Combining like terms, 10n plus n, I get 11n. So my result is that the product of these two binomials is equal to 5n squared plus 11n plus 2, which is exactly what I wanted. So I've completely factored this trinomial. Okay, so in this part we're going to learn how to factor polynomials with two variables, but let's remind ourselves how to factor a polynomial like this one that just has one variable, x, in it. Okay. First thing I notice that there's a GCF here. I can factor out that GCF is 2, so I factor out the 2. Then I look inside the parentheses, I notice I have a difference of 2 squares. This is x squared, this is 9 squared. So a difference of squares is equal to a product of conjugate pairs, so I write 2 times x plus 9, x minus 9. If you've forgotten this pattern already, what I recommend you do is foiling this, and you will see that you get x squared minus 81. So what if I have something like this? Notice I have two different variables. The procedure is exactly the same. Notice that they both have a GCF of 3, so I factor that 3 out. Once again, I have a difference of 2 squares. I have m squared minus n squared, so I can factor this as 3 times the conjugate pairs m plus n times m minus n. Okay, so if I wanted to factor a perfect square trinomial with more than one variable, I can just use the exact same patterns that I use with perfect square trinomials that involve only one variable. Okay, so I could factor this perfect square trinomial in the following way, except for there's actually a minor error here that I need to fix. The factorization of a perfect square trinomial is a plus b times a plus b here. Okay, so this perfect square trinomial I'd actually factor in this way, and this perfect square trinomial I'd factor in this way. So I would use these patterns the same way I've used them with perfect square trinomials that involve only one variable. So let's suppose I wanted to factor this trinomial completely. Okay. First thing I want to look for, once again, is the GCF. Notice that all three terms have a GCF of 3 and nothing else, so I factor out a 3, which gives me the following. And then I look inside here and I see that this is indeed a perfect square trinomial. So I use my perfect square trinomial factoring pattern to write g squared plus 4gh plus 4h squared in the following way using the pattern. And what you want to do is you want to make sure that that you factor completely just by foiling in reverse, and you'll see that that's the case. Look, if I multiply g times g, my first product, I get g squared. My outer product, g times 2h, which is 2gh, plus my inner product, 2 times gh again. So I have 2gh plus 2gh, which gives me 4gh. And my last product is 2h times 2h, which is 4h squared. And of course I can write, since I have the same quantity being multiplied by itself, I can write this as 3 times that quantity squared. Alright, let's look at another example here. First thing I want to do when I'm factoring is take out the GCF. So notice that 3 divides all 3 terms in this polynomial, so I factor that 3 out, which results in the following. Okay, so let's see. Is this a perfect square trinomial? No, it does not look like it because this term right here does not have an even coefficient. So let's see. How would we factor this? Okay. Well, if you remember, if I factor something in one variable that looks like this, trinomial that looks like this, I look for factors of 12 and I add those factors up and see what the sum is. Now the sum, when I factor something like this, the sum of this number, the sum of the factors of this number should add up to the coefficient of this term here. So 1 and 12, while those are factors of 12, they don't add up to 13. Or they don't add up to 7, they actually add up to 13. 6 and 2, similarly, they add up to 8. 4 and 3, that's what's going to work. 4 and 3 multiply together to give me 12, and add to give me 7. So I would factor this trinomial as x plus 4y, x plus 3y, and of course you can FOIL to check. If you notice, my first product is x times x, which is x squared. X times 3y is 3xy plus 4xy, so I have 7xy, which is what I wanted, plus the product of my last terms, I have 4y times 3y, that's 12y squared. So I know that this is the correct factorization of this original trinomial. Okay, so let's show an example of factoring a polynomial using grouping. Once again, I look, do all 4 terms have a GCF greater than 1? And clearly they do not. 2 divides these 2, but it doesn't divide these. 9 divides these, doesn't divide the last 2. So the GCF here is 1. So it doesn't do us any good to factor out a GCF of 1. So let's take a look at what we can do next. Let's group the first two terms and the last 2 terms, like shown here. And then, just like before, I look for the greatest common factor of these 2 terms. Notice that 9 divides both. Not only that, but both of them have at least one factor of x. So I'm going to factor out 9x out of the first 2, giving me the following. Notice here that these 2 only have a common factor of 2, so I factor the 2 out, giving me the following. So, let's take a look at this. Notice that inside the parentheses I have x squared minus y, and over here I have y minus x squared. If you recall from earlier lessons, these two are called binomial opposites. So if I factor out a negative 1, I could rewrite this as negative 2 times x squared minus y. I want to do that because I want these two factors to look the same so that in the end I can factor them out. Okay, so if you have any doubt as to what I did here, whether or not this expression is equal to this one, you can just go backwards. Okay, if you notice, I have negative 2 times x squared, which is what I started with, and I have negative 2 times negative y, which is positive 2y, which is also what I started with. So I know that this entire expression is equal to this entire expression here. So I haven't made any mistakes, and I encourage you to check your work along the way in the same fashion. Okay, so notice that these two terms, this term here and this term here, okay, both have a common factor of x squared minus y. So I use a distributive property in reverse to factor that out, and I get 9x minus 2 times the quantity x squared minus y. Then I look inside both factors here, and I see if there's any more factoring I can do, and there definitely is not. Okay, so the essential question we addressed is how can you factor polynomials that have more than one variable? Use the exact same methods that you use for polynomials of one variable. The difference of squares or perfect square trinomial patterns, sum of the factors method, or factoring by grouping.